and he will tell us about walking phase transitions.
Okay. So thank you very much for the opportunity. And we'll be talking about this work which I did with my student Miguel Van Wassenaar. And so first slide is sort of motivation why even considering walking through phase transition is that one of the possible solutions to the Higgs hierarchy problems comes from the models with strong dynamics. Higgs is a bound state of some new strong interactions. Now then, if I look at the constraint from flavor sector, then we see that we have a top sector which is heavy, top mass which is heavy, top is heavy. So we would expect its scale where it's generated to be very, very low. At the same time, we would like to have light parts to be generated at a scale which are much, much higher. And so then because if there is origin of flavor at light scales, then we will have probably at the same scale, we might expect flavor violating interactions. So, and then these are ruled out by orders and orders of magnitude. The solution to this came out, I guess, in 80s, and it's called walking technicolor. So idea is that if the dynamic is walking, so theory remains roughly the same for very, very large separation of scale. So this is why it's called walking. So that's why considering walking transition in walking dynamics is interesting. And then why we should have this type of phase transition? Because if we have this new sector which confines, we now live in confined phase, and before it was deconfined, so there will be this confining transition from when this new strong sector was not confined. And you know, this phase transition can lead to the very interesting phenomena in early universe physics, which might lead to some observational signatures today. Now, how attack such phase transitions? So since we are dealing with strong dynamics, the best thing to do lattice, and there are numerous lattice simulations who are attacking the problem for beyond standard model physics, and they're looking at the scenarios with walking phase transitions. However, I think we are still far from conclusion, so this is ongoing study. Another way to analyze phase transition in this type of model is done with holographic models, where people were looking at Randall-Sundrum-like scenarios. And there you can calculate some properties of the phase transition, in particular when there is a one light mode which corresponds to the size of extra dimension. It's called dilaton, and if this dilaton is much lighter than the rest of the fields, then you can calculate more or less properties of the phase transition, which is good. However, what we decide to do in this paper is a bit different, right? So there was the idea that walking dynamics occurs when a beta functional system has a complex fixed point, which has very, very small imaginary parts. So it's a conformality lost idea by Kaplan and Damtison in 2009. And recently it was reviewed by Richkov, Gorbenko, and Zan. And what we did, we looked at some toy model, which is perturbative, and where this complex fixed point condition is realized. So what's this complex fixed point condition, why it's relevant for the walking dynamics? And so let's consider a gauge theory with fermions at fixed number of colors. Then we believe that there will be some conformal window, right? So I change, now let's suppose I change number of fermions is the parameters which I change. And I know if I cross some value, I will lose, if I keep increasing number of fermions, I will at some point lose my UV freedom. Once I pass this number, which I call NF plus, there will be this Bank-Zaks fixed point, which will be perturbative, where beta function of gauge coupling will be vanishing. Now let's suppose I will keep decreasing this NF. And at some point, if I will decrease it enough, I will lose this, at some point, Bank-Zaks fixed point becomes non-perturbative. And if I keep reducing number of fermions, at some point, I will pass some value, and theory will lose this fixed point completely. So what's going on? How this the loss of disappearance of fixed point is going on? And this is still not understood, but there was a conjecture, and that what's going on is that we have two fixed points which annihilate with each other. And after this annihilation, we have a so-called complex fixed point. So let me consider, example of very toy example of fixed point annihilation is, let's consider a coupling in the, let's look at the evolution of this coupling lambda. And let's suppose it has this form. Now, if y is my parameter, which I change, it's my theory parameter, like number of fermions. So if y is negative, I have two fixed points, and y is attractive, another is unstable. Now I keep it increasing, and when it crosses 0, I have just one fixed point, and then I have when two fixed points collide, and then when I become positive, I don't have any more fixed point. However, formally I can call this fixed point complex. And let's suppose what's going on, let's look at the evolution of this coupling when I have a complex fixed point. You can solve this equation, and you'll see that near this so-called fixed point, near y equals 0, evolution of lambda coupling near value lambda is very slow. So the theory remains roughly the same for a very large scale separation. And you can solve it, and roughly for the scale of 1 over square root of beta function, theory remains with the same coupling. So I have this walking-like behavior if I have complex fixed point. This scaling of scale separation, 1 over square root beta function, is often called Miransky scaling in technical literature. Now, so what's the model of, so ideally you would like to analyze this type of model on a lattice where you have some Lagrangian, where you have only gauge field and fermions. Now, of course, this is very hard, but to gain some intuition, recently there was proposed this by people in CISA, Benini, Cerrone, and Jossa. They proposed a model which contains scalars. So model is based on some SUN group, gauge group, and it contains an F-Dirac fermions. And on top it has a scalar field with two types of coupling. One is double trace and another is single trace interaction. Then if I look at the beta function of this theory, you can, it will exactly have the behaviors that we would like. So for example, analysis of beta function equation becomes very simple in Veneziano limit when I take number of colors and number of flavors large. Then condition for fixed point for gauge coupling and for interaction H, which is this trace, become independent, and I can solve them. And now, depending on let me fix number of colors, and depending on number of scalars and number of fermions, I can make this beta function for coupling F to contain, to have complex values. Now, of course, as soon as you see scalars, you can say this is, you are going back to hierarchy problem, because we don't want to have elementary scalars, but at least, so this is indeed the case, but this at least allows us to learn something about working dynamics. So of course, model is perturbative. Now, and this is a plot which sort of illustrates this phenomenon of fixed point annihilation. So they vary parameter number of colors, and so these are the position of fixed point in the coupling space. So you can see at some point fixed points collide and they disappear. So I have 4 fixed points that collide. And in particular for this model, the fixed point disappears when number of scalars divided number of colors is equal to this value. So the model exactly has this working behavior, and this is a solution for if you solve for coupling as a solve RG. And the minimal number of colors and field content which allows you to have this model at work is you need at least 25 colors. It's a large number, but that's what it is. And you need 2 flavors of scalars, but number of fermions you need very large to have everything happening at weak coupling. Then indeed, if I look at this, for example, F plus H coupling evolution, you see this very long working plateau. Of course, the size of plateau is way above what is needed for weak Planck hierarchy problem, but it's an illustration that model can work. So for various numbers of fermions, we have various sizes of plateau, but in general, we are getting this walking plateau. So what we decided to do is let's look at the phase transition in this scenario. It's under control in perturbation theory, every couplings are weak, so we can calculate everything, more or less. Of course, it's good, but then how you would like to apply the results you obtain to more realistic theory without scalars, because no, you don't care about working theories with elementary scalars. It's not clear, but I think some of the features which we see might be true for the models without scalars. So how the symmetry breaking occurs in this scenario? So we don't have chiral symmetry breaking, but we have a symmetry breaking. So what's going on? So this is the potential. And if so what controls the positivity of potential is this combination of couplings. And this is exactly the combination which is positive in UV, then it has this walking plateau and then it drops. So when it becomes negative, it immediately will have breaking of my gauge symmetry from SUN to SUN C minus NC minus NS. It's some analog of chiral symmetry breaking, so we don't have it. However, at the point where this sum of two couplings F plus H becomes 0, there will be one mode which will have mass, zero mass at 3 level. So this mode is sort of scalon, it will be lighter than the rest of the mode particles. However, its mass is 3 level, or it's 0 only at 3 level. At one loop, I will have usual common Weinberg potential, and I can calculate the mass of this scalon, and it will be equal proportional to the beta function of this F plus H couplings. And note that it will be proportional to the beta function of these couplings at these exit points, not during the walking, but the point when I have symmetry breaking. You know, I mentioned in the introduction of the talk that previously there were a lot of studies of this phase transition in holographic models. And pretty much holographic models in the limit when I have light dilaton. And in this case, potential is very, very similar. It's also a Coleman-Weinberg-like potential. However, there are a few, I think, differences which are important to highlight. First is a scale separation between UV and IR. So in this walking like behavior, the separation is controlled by 1 over square root of beta function. This Miransky scaling. At the same time, with in Randan-Sundrum-like models, the separation is like 1 over beta walking. However, this is not so important for phenomenology. What's more drastic difference is that in this perturbative walking dynamic case, the dilaton potential and then potential which controls the symmetry breaking phase transition is fixed by the beta functions, not during walking, but at the instance when I have symmetry breaking, which is quite different from the beta function. At the same time, in RS-like scenarios, it's beta walking. So dilaton in this type of models is generically much heavier. So this is important feature, and this, I can anticipate, leads to the quite strong modifications of the properties of the phase transition. Okay. So what we decide to ask is, what will be the properties of such phase transition? The transition will be of first order, and we heard from you from first talk that it might be a good signal of stochastic gravitational waves. No, it's okay, but there is one thing is that in our construction, we have a lot of fermions which we needed to have coupling under control, but these fermions remain massless during phase transition. So there is this feature which will not be the case in the materialistic model. So it's another issue which we should remember when interpreting result. Now, for Coleman-Weinberg-like theories, it's signal is quite strong, and you can, I don't know, if a future experiment can test the scale up to 10 to the 10 GeV, so which is very, very high above all the possible collider experiments. So which is, something which excites me because, these are exceptionally high scale, and if we can test them, it's very, very important. So let's see what we will see with what we will see in these perturbative walking scenarios. So to calculate it, we decide, again, our model is perturbative, so we look at the effective potential. You heard it in the previous talk, and we use truncated full dressing, so we sum thermal masses. Now, to calculate this tunneling amplitude, we need to know the potential very, very far away from the true minimum. We need to know it here, right? And in this region, in the origin, you need to remember that loop expansion for thermal loop expansion, it's controlled by G times square root number of colors. So this thing, if we would like to keep our theory fully perturbative, it pushes us even stronger towards smaller and smaller values of couplings. Now, another issue of our models at very, very low temperature, here we are hitting Landau poles. So we would rather have our phase transition to happen before this thing happening so that we can trust our calculation. So what we did is then, okay, tunneling property you can calculate using it's a usual, using shooting method, it's a usual 3D and or 4D bounds. And in our case, we find it is dominated by 3D bounds. Now, another issue is that we have a lot of scalar fields in our model. So ideally, you should calculate multi-dimensional bound solution to find the tunneling probability. But in our case, the fact that helps is that only one field, scalar field, has a vanishing tree-level potential. All the rest of the fields, they have positive tree-level potential, so the bounce direction will be exactly along this scalar dilaton field. So the calculation is very, very easy. It's trivial. And these are our results. So we stick to the minimum number of colors and scalars, which gives us working behavior. And this is a value of 3 over T over temperature. So you can see that depending on number, so these numbers are number of Fermis. So depending on the number of Fermis, we can get very, very different behavior of this bounce action. Now, what's going on is that in reality, so the number of fermions changes the value of gauge coupling, right? During walking and also at the symmetry breaking scale. Now, if gauge coupling is very, very small or Kolmogorov potential becomes very, very flat, dilaton scalon field is very, very light, so action becomes very, very large. At the same time, as couplings are larger and larger, potential becomes less shallow and tunneling can happen much faster. However, again, you cannot go too much above, below this 120, which is this line, because at this point we are stating, again, our model becomes non-perturbative because thermal loop expansion becomes not under control. Now then, okay, roughly phase transition happens for S over T around 100. So you can see this even doesn't tunnel. We don't have phase transition for this line. But okay, as we heard in the previous talk, pretty much gravitational wave signals are controlled by these two parameters, let's say roughly. One is how much energy do I have, and another how big will be bubbles. So the bigger radius of the bubbles, the stronger will be signal. Now, in our case, the faster, larger couplings is the phase transition, the weaker will be the signal. So, yeah. So the lighter is the dilaton scalon field, the stronger will be the signal. So let's consider, so what's going on with this case when I told you that 136 and F equal 136, so action is very, very big. Tunneling rate is very, very slow. And this is exactly what people have observed in Randall syndrome-like models. They also have very, very light dilaton. And again, the reason is, yeah, dilaton is very light, so potential is super flat. And what was suggested in various studies that, you know, this one indeed cannot tunnel, but maybe there is some another physics effects which can modify this action so that tunneling can happen. For example, a recent idea was to use QCD effects to drastically reduce this action so that tunneling can happen. Now, calculating gravitational wave signal, so what important thing is to what will be energy distribution between various contributions. And here what's important is that, so there are two contributions, one is from scalar field and another from sound waves. However, the scalar field contribution becomes subdominant if the bubbles reach terminal velocity, start expanding with constant velocity, because at this point, energy which is stored in the field configuration scales as a radius squared of the surface of the bubble. At the same time, total energy is volume, so this fraction of energy stored in the surface vanishes. Now, to understand whether this runaway behavior can be achieved or is avoided, one should look at the next to leading order pressure effect, because leading order pressure effect was shown are independent of the velocity, but next to leading order effects can stop it, so there is this effect. And these are our results, so we look at the various reference points for our model. And we see that so for large couplings which is heavy dilaton, the transition is mostly dominated by plasma effect sound waves, gravitational wave origin, and then it starts disappearing signal because transition becomes faster and faster. And at the same time, if I keep increasing number of fermions, my coupling is smaller and scalon is much lighter. So the effective effect comes mostly from scalar field published wall collisions. Now, the thing is that even though you can see that increasing coupling, reducing number of fermions, we are going towards smaller and smaller signals, our model becomes non-perturbative. So we are in a situation where perturbativity forces us to be in this region where signal is big, but it doesn't. And this brings me towards summary slide. And so I can tell you that we have studied phase transition in this perturbative class of models. And we can see that we can get very, very different scenarios for phase transition depending on the properties of the exit from working dynamics. So pretty much what was controlling the physics and phenomenology was the properties of the exit from working dynamics. Now, okay, this is an artifact of our model. That model is perturbative only in the region where we have some signal. We have tendencies that reduction of, once we have larger coupling, the signal is reduced, so transition becomes fast. Of course, what we did is the analysis of a toy model. So, we have scalar fields which shouldn't be there, but I think this feature, the heavier dilaton, will be smaller, you will have smaller signal. Okay, it was known, but still that this feature that the phase transition is largely controlled by the exit from working dynamics properties will be true also in realistic models. So, thank you.
Okay, thank you. So we have time for questions.
I have one question. Can you hear me?
Yes.
Yes. I just curious, do you have any plot about the wave of the scalar over the temperature dependent wave over the temperature? The V over T?
V over T is, okay. So okay, I don't have it in the slides, but V is, okay. I can, so in the model, I can go up to the 10 minus 5, from order 1 to 10 minus 5.
I just curious to see any interesting trend when you change the number of flavor.
So the point, yes, okay. So let me go to this slide. Yeah, I should have put it. So once I increase number of flavors, I am getting coupling becomes smaller. So V over T becomes much larger because nucleation temperature drops. Because V is order 1. Nucleation temperature, you can read from this plot, it's roughly crossing with this line. So,
yes. So
yeah.
Yeah, just curious to see when people talk about that complex CFT, they say that's like a weakly first order phase transition. I'm trying to say whether you can use a V over T as a diagnose to know how weak of the first order phase transition.
So Now, okay, so here it's two things which are important, right? For critical, so the point is that V over T critical is always order 1. However, the potential becomes very, very shallow in this case. So if I'm looking V over divided by T nucleation, this can be very, very large. So V over T critical is always order 1. However, you don't tunnel at T critical, you cool down a lot because potential is very, very shallow.
Thanks.
No, actually, I have a question. So in your model, the phase transition always completes?
You know, if so for 136, it doesn't, this line. It's exactly what was found by Ratazzi, Nicolis, right? It's RS idea. So it's so flat that you can never do it.
Yeah, I think for different reasons, because...
No, effectively, it's the same reason. The potential is super flat.
But it's also the size of the bounce action, which is increased by this n, which is large.
Right, but here we also have large n, but at the end, what matters is the flatness of potential. So when you have very, very flat potential, then you cannot tunnel.
Okay.
Not flatness, it's shallowness.
So other questions? So maybe I have an extra comment. So
Sure.
in the paper of Rishkov et al. That you mentioned at the beginning, I think they were arguing against the existence of the light dilaton below the...
So, okay, so I can answer this, right? In this, okay, where it is. So this is a result, right? So where it is, yes, this one equation, right? So in my case, my dilaton is a beta function of symmetry breaking scale here. And beta function here is big.
No, this I understand, but I'm asking about the strongly coupled case.
Hold on, now I'm saying, now the thing is that now I can tune this beta function at exit scale to be small as well. And so that's how I was getting light dilaton in my result. And you know, it's sort of accident that model becomes perturbed, calculation is full under control when dilaton is light. Otherwise, yeah, generically dilaton is not light in this construction. However,
so in coupled case,
I cannot do thermal theory, right? It's model is perturbative for 0 temperature, but I increase temperature and perturbation theory breaks down quickly, faster.
but it goes in the direction of a heavy dilaton.
It goes the direction of heavy dilaton, right? But then I lose perturbativity, so all advantage of this perturbative model, you lose it.
Cool. Any other question or comment? Okay, so thanks everybody, and we'll see you next week.